For those who do not have GPU, NVIDIA GPU at home, you can actually use OLED to do this exercise. So what you need is to go OLED. I think some of you must have learned this before, because I heard from the other group. You have this. Some courses that use OLED. Is that true? You use OLED before? Never? Once you get here, you can actually open up. If you have notebook before, you can just go to Google Drive and open it, or the recent one, which will appear there. Or you have GitHub, you can actually commit your new notebook inside there if you want to. Or if you have a downloaded one, then you can install this IPython on the PC as well. Right? But what that actually is a cloud service, where you can upload your notebook into your cloud service and run on the remote computer. So you have the PC that is here. So it's a PC, and you are connected to the cloud. Sorry, this is the internet, and this is the cloud. Cloud service. Basically, you're opening up a compute instance here. Okay? So your compute instance is going to be just like a PC. It's a remote PC, but you can view it through your PC. Okay? But then whatever computation is done on the compute instance. So you can spin off the compute instance by just clicking new notebook. Okay? Or you upload your notebook, or you open up your notebook inside the Google Drive. Okay? So you spin up quickly, and you can use the computer remotely from the PC. So your PC is just like a dumb terminal, showing you the interface to this PC here. Okay, we can control it, but we are not going. We cannot. I don't think we have any graphical user interface except for a very simple one. Most of the time, we'll be dealing with the command line interface. Okay, I will show you how to do that. Or write a program inside the IPython node in order to do your operation, whatever operation in Python. Okay? So for now, because you might not have a new notebook, just click there, notebook. And give it a name.
Collaborator.
Okay, you can give a name here. Let's say, maybe 3 GPU. This one will be printed inside the Google Drive automatically, but if you want to relocate it, locate in a drive, and you can move it around. If you don't want it to be here. Okay, you can move it around, let's say organize, move. I want it to be here. Here is basically the notebook where you can type in Python program. All of you must have learned Python before, right? Have you learned Python? You learned Python, right? So you use this notebook, you can write Python. For example, you want to print something. In Python, you must print the whole world. This is a notebook for Python. We can write C program, I'll show you how. It's not so straightforward, but it can be done. Okay, so when I play, I think I have to initialize first. First I have to create the compute engine at the back end. Now we created already. Now we run the program. You can see hello world. Alright. Okay, so that is first Python program, but we're not going to write Python. But you can write Python code to automate your process if you want to. Okay. If you want to automate your process, you can write it in Python script. Okay, for us, we want to do that. We want to use NVCC, which is the NVIDIA C ParallelComputing. Okay, another thing, apart from code, you can actually write text. For example, this is first check NVCC. Okay, you can write text like this. And what is shown here is what is going to be displayed. If you don't like this to be small letter, you can change it to bigger letter. You can bold it. The equalizer is up here. You can do whatever you want. Once it's done, so this is the text that's appearing. Okay, with this code, you want to move it down. Just click this button. Then we go down. Okay. So right now I want to check if MVCC is available or not, which is the comparative chain. I can add the code here, or I can add here, it's up to you. I can add here. You can move this one up. And to run the command, you have to put exclamation mark. Okay, if you don't put exclamation mark, that is Python statement. So you interpret it as Python statement and use Python interpreter to run. But if you put exclamation in front, it's basically passing your command to the Linux bash. Bash is a command line interface for Linux, which is like our command prompt. But Linux use bash. Okay. All the compute instance was created, they run on Linux, not Windows. So we have to use Linux. So exclamation mark, NVCC, and I want to know what version that compute instance that Google use. So I can press this button, play. And then it will start to give me the information, the version number of the NVCC video. It's not on our PC, this is the PC on Colab. Okay, so they have this compiler to chain of just the latest version 12. Version 12 is the latest one. Alright. And okay, if you want to delete this, just click here and then let's say I want to add here try simple. Okay, before you put, if you can actually upload the code here, you can upload it by clicking on this file symbol, folder symbol. Okay, and then you can upload it. Here you can see the upload icon. You can upload the program if you want to. Okay, but I suggest not to upload because if you upload, it will not be in your notebook. So when you close the program, you go back home, you're not able to get that file again. That file will be disappeared because this file, when it's uploaded, it goes to the compute instance. The compute instance is just like a computer, but without storage. Once you close it, whatever that you uploaded is gone. So I suggest that you write your code inside here. Okay, so that every time you use a notebook, your code is always there. And you just need to play in order to bring it into the folder. Okay, let's see how we do it. Now, the exclamation mark means you pass this command next to the exclamation mark to the bash command line interface to execute it. But if you want this notebook to create a file, we put percentage twice. Percentage, and percentage twice. Percentage, and I want to write file, so I'm telling the notebook, I want to write file. And when it recognizes it, it becomes blue in color. If it doesn't recognize it, it will be black. So you know that it doesn't understand your notebook doesn't understand your command. Okay? Alright? So without anything, it will be considered as Python statement. With exclamation mark, the command will be sent to the dash. 2%, that is the command for the notebook itself. Okay? So we tell the notebook we want to write a file. Let's call it simple vector. Let's see. We want to write this file. And when you press enter, you'll allow you to type in somewhere. So I'm not going to type the program, I'm going to type and paste it somewhere. I want to do this exercise, simple one. You come from here. This website. You go there, and then you can copy this. Okay, so this is the file. And just paste it there. Okay, one thing that I want to change is this one, because actually it works still with the double quotation, but I prefer to change it to the proper one. Okay, because I know that this filter runtime is inside the library header file, that folder. Okay? It will not be anywhere else. So I put this under bracket. If you put this quotation mark there, double quotation mark, it means that check inside this folder first. But we know that this is not going to be inside a folder, right? It's inside the library, so we put that in the bracket. Okay, this one is safer. If you put like this, it will work still, but it's not as safe. For example, if you have filter runtime header file inside here with the same name, then you will use yours rather than the one in the library. Then it might mess up with the system. In order to avoid it, we use this the bracket. That's why I changed it. But for our case here, actually, with or without, it doesn't matter. But this is a proper way to do it. Okay, so this is our file. That's why we put double quotation, because this file will be looked for by this compiler in our creator, which we haven't created yet. We'll create it in a short while. Okay, here I write in the file. Once you click it, you can see it appear here. It doesn't appear, click refresh. Okay, so right now, when I play, it will create this file in my folder. So my computer system can see it right now. Okay, and we're going to compile this in a short while, but we need some more file that we want to write. Here we have more. Here we're going to write file again, but this time is the header file. We need another two more header file. Here in this header file, basically is this copy it, paste to here. That's all that we need. Oh yeah, because I use a different name, so I'm going to copy this and paste it. Okay, the original file is copied up and I changed it into another name. I call it simple one. Play again just to update it, and then play here. Now you can open this file from this panel here by double clicking. If you double click, then you see the file on the right hand side. But right now with the color annotation annotated for you nicely. Here it's all black and white. Here is with color annotation, so that you can see which one is command, which one is a special keyword, which one is a variable. Okay. That if you change here, it will appear. The change will, if you save, it will appear directly immediately in the folder. but it will not change your notebook. That means when you close your notebook and you go elsewhere, you open up your own notebook again. Whatever changes that you made there will not be saved. If you want to save it, you must change it in your notebook. Okay? So I suggest that you change in your notebook rather than because whatever changes that you make there, it will not be updated inside. Okay? Okay, here is just to check whether, for example, if let's say I put this here, right? Now here it doesn't change immediately unless I play. Then when I play, of course it doesn't change still. I have the double click on it and now it's saved. That means whatever open here is the old copy unless if you update it, you have to reopen double click it to reopen it. Okay. And you have to play it. If you don't play it, it means you will not update it. Okay, next, once you have this, the last one is I want to create another file. And this file is this file is this one. Okay. Is name, the name file. It's called p.s. So copy that. P.s. Zero. And I copy this profile here and all content here, and I change this because I changed to this name already, so I'm going to change that as well here. Okay, once I've done that, so this program is actually a working program. We will verify that. We're going to print the result. The result should be 14, 12, 7, right? 12, 14, 7. Okay? 12, 14, 7. Print out on screen. Right? So let's play this. Play this is not running the program. Play this is just to write the file. So here. So play first. Right here. Right? Now how do you run the program? Before you run the program, you have to compile. Okay, it's unlike the Visual Studio. Visual Studio actually is a integrated development environment. To make it simple, you just need to click on the button to compile and to run the program. But here we have to use a command line interface to do everything because we don't have the IDE in this case. So how do we compile and run? Okay, in order to compile, click this. And again, we want to send the command to bash is exclamation mark. Right, and VCC is the compiler name. You can use the normal CC compiler, but unfortunately in Linux they don't have Visual Studio, Visual C++, but they have other compiler, either Clang, CLM, CLANG, GCC or G++. So you can choose anyone. Clang is a new C compiler used by Apple. Apple actually wants to create a new one, so it's Clang, and then GCC, and then G++. Now Clang is C++. GCC is for C. G++ is G. Yeah. Right, whichever one that you want to use is fine, but I think for our case, because it's C++, so I suggest that you use G++. Okay, you can use G++ here, but if you use G++, it's only compiled for the CPU. It will not be compiled for the GPU. If you want it compiled for the GPU, you cannot use this because you use NVCC. Okay, so this one is for C++, but it's for GPU and CPU, both. Okay, both for CPU and GPU. This way we're going to use MVCC, and I specify the output. Let's call output with a shorter name, simple vector S1. Simple vector And you can use .exe here, but exe is only used, I mean the extension is known in Windows and DOS as executable file. But in Linux we don't use exe. You can name exe as well if you want to. But it's a better known extension. The better known extension is .out or .o. Okay. This is how they name it. It's up to you what extension that you want to use. But the common one is .out, so I use .out. Okay. And this one is output. That means the file that is going to be written as the executable file that is going to be once it's compiled, it's going to write to here. And when I run this program. Okay. But what is an input file? Input file is this tree. But one of them is header file. Header file you cannot compile. You can only compile the program. So the program is in .c, right? So there are only two .c. So you have to copy all of them. It is. The order is correct, whichever order that you want. It's not really a big problem. You can start with simple vector at first, or filter test one first. Okay. But two of them must be there. Okay, so there are three file names. The first one is because of this -o here, indicating that this is the name that I want to use. Okay, for the output. Followed by the input. The input, whatever input that you want, you just add it behind here with a spacing, or at least one spacing. Okay? And you understand that that will be the input file that you want to compile. Now you cannot compile only one, you have to compile all. Okay? You can compile one, but you cannot put this -o. Okay? You have to put -c. It is compile on it, but not creating any output executable output file. Because you want to create the executable output file, you have to compile all of them together. But if you want to compile individually, you have to put -c. That's just compiling individual file, but does not generate the output file. You just generate an intermediate object file. Okay? So now you say I want to compile and also produce an output which is executable file. You have to put all of them together. Okay? So compile it. If there's error, you come up error. If there's no error, you just empty. There's nothing there. This tick here, it does not respond. It means that it's okay. Right? Now I can run the program. Now to run the program, normally we do like this. We put a dot, slash, and then SVADR. Okay, you don't have to put also can, but I put it here because I'm telling Bash, run this program which is in this folder, not in any other folder, only inside this folder. Okay? Because there can be any other file elsewhere. Okay, here is here. So you look for this folder first. If you cannot find it, go and find somewhere else. But if I put /, it means that I'm telling Bash, don't look elsewhere, look in this folder. Okay, if you cannot find, then don't go and simply go and run any other program. Okay, you just generate error, tell me that the file is not there. Okay, otherwise you go look at other folder, and if you find one, then you execute it. Okay, and this can be a confusion because maybe somebody else put this file in another folder, and then you're running the other file. Then you say, how come the output is different? Okay, it's because of this folder. So here I'm forcing the Bash to look in this folder with this file. If you cannot find, then don't find anywhere else. Just generate. Okay.
My one book over.
Oh yeah, because I changed the file name. If you see an error, CUDA or something, right? Because I changed it already.
Oh.
Yeah, I changed it. So here also change it. Change this as well. Yeah. Because I changed the name. Okay, if you have any error, let me know. I'll have a look. Now, right now I can run the program, and it should show me the result, and the result happens to be 0, 0. We know that this result is wrong. The result should be 14, 12, 14, 7, right? But we got 0, 0, 0, why? Because the GPU is not enabled. Okay, the GPU is not enabled, so I need to enable the GPU. So how do I enable it? Go to the runtime, go to change runtime type, and you can see there are a lot here. These are all GPU as well. This one are modern NVIDIA GPU. It's disabled because we don't have, I don't pay it, and you also don't pay you don't pay it. So we cannot use the latest GPU by NVIDIA. We can use the old GPU, Tesla 4. This is not the car Tesla, it's the GPU is called Tesla 4. Tesla 4 GPU, and these are old GPU, the latest one is the other two there. And just click on it. And then click save. Now, when you click save, you
change runtime.
Something happened. I think I did not show you the warning. The warning says I okay, it's not. The warning tells me that when you enable the GPU, and the GPU is not available in the old compute instance, so it tells me that I will close this and I open another one in another computer. So there's another computer here, another compute instance here. Okay. So this is without the GPU. This one is with the GPU. So it migrated my file just now, which is my notebook. It only migrated my notebook. It did not migrate my file here. So just this first experience by you maybe the migration that is happening. Okay? I think I talked about it last week about migration, right? The code is migrated, not the data. Only the code that is migrated here. So it tells me that here no GPU. I have to open a new one for you. And then you close down this compute instance. And then you migrate my notebook into a new instance. Right now I'm in a new computer. And this computer has a GPU. But it did not migrate my data, that's why my data all missing. Right? Now in order to bring it back, you have to play this again. Go back there and play. Play this, then here. Okay, and play this, and play this. You don't have to wait for them to complete. You can play all of them at once because it's multitasking. And the file will be there. So I forgot about this. Play this as well. Then this file will be there. So every time it does the migration, it will tell you first, I will go to migrate because of some problem. Maybe it doesn't have the resource, I have to migrate. So once you click OK, you migrate, and you have to do this again because notebook did not migrate. That's right. Collect does not migrate the data in the folder. You only migrate my notebook. Okay? Right? So this, you can see the migration is very fast. Of course, there are more complex migration where we can migrate not only the notebook, also the data itself. Okay? This is the simplest one. Here, the more advanced one, even your program that is running, when you do the migration, it still retain the execution. It means whatever you have executed in the past will continue here without you knowing. Okay? So that is a more advanced migration, and there is such a system. Okay? So you migrate from one place to another without you knowing that the migration has happened. And this can be important, like for example, in our case, resources not available in here, you have to migrate to a new system. Or they detect that the power failure here, or maybe there's an earthquake, let's say in that particular area, they can migrate automatically without you knowing it that your system already migrated. Okay? Let's say you are using, for example, Google Drive, or I should say maybe IoT, let's say IoT or something like that. It might be running in the cloud, and it can migrate from one place to another without you knowing it. Okay? Now, of course, you have to pay for that kind of service. Okay, so now I already done that. I have to compile again because the data was not migrated. Then play this. If there's no error, you just keep silent, and then you run this. You see 14, 12, 14, 7. Okay, because right now the GPU, this compute instance has the GPU. Now you use the GPU to display the result. Okay. So if you see something wrong, remember to go to the runtime there. Okay, be prepared. Huh? When you click OK, you migrate whatever you did not save, it will be gone. So I suggest that's why don't open up here to edit. You edit in your notebook because whenever you migrate, your data is still there. Okay, you don't have to save. This notebook will be saved automatically by program. Okay, now so just now when I click here, I have to wait and I have to check for this thing here, there, only I click here to run, right? But sometimes you don't want to do that because you have to click twice and do it. Or maybe you can click and click like this. But I suggest a better way is actually combine this together. Okay, you can put on the next line, like that. Okay, delete this. So instead of 2 code, it's only 1 code. Just like happens to be in 2 lines. Okay, in this way, you will execute the first line, in order, from top to bottom. You compile first, once finished, then you will run the program. Right? So if you do that, then it's much easier. Just click one time, you compile and run. Okay, compile, and then run the programs. Okay? The result comes out straight. Okay? This one might be more practical if you want to use it this way. I think it's good. Okay, next I want to do profiling. Profiling also sent to the dash MV12. That means NVIDIA profiling. And also the same following, so I just do multiplication. Okay, profiling means I want to profile how measure or gauge how fast or how much time there is used or how much resources there is used in which area of the code. Okay, so I use the NVIDIA profiler to show you. Then when I click play, you run the program at the same time profile. Of course, you have to run the program, otherwise you cannot profile. So you can see you run the program and you get the result. And then apart from that, you also print out the result, the profile result. Okay? So what does it show there? Okay, the first 3, actually it can be more, is the GPU activities, and the rest is the API calls. The first 3 is actually the program that is run in the GPU. That's why it's called GPU activities. And all of this percentage, when you added up, is 100%. Right? So the first one shows to you it spent 53% of the time in the vector addition kernel. Okay, 25% in mem copy from device to host, 22% roughly. Also mem copy from host to device. So actually the mem copy itself takes up about 50% of the time. The other 50% is to do the vector. And the reason for this is because our problem is very small. Okay? But if our problem is big, then this one will be small. Okay? That means it's not wise to actually use GPU if your problem is very small. It's just trying to tell you that, right? So your program is very complex, then it's more suitable to be solved by the GPU. Okay? Now, how about the API calls? The API calls is the function that is called by the CPU. So this is how much time the CPU spent doing the job. So QWMemo actually takes a lot of time to allocate memory. It takes a lot of time. That's why I told you that if you allocate the memory, of course you have to free it, but if you reuse it, then don't allocate free, because you see how much time that is spent just to allocate. 90%. Of course it's quite, actually it's quite slow as well. It's 97.17 milliseconds. Compared to GPU uses 4.5 microsecond, right? So QDAP analog actually is very expensive process. Okay. Now we know how to compile. Okay, so right now I pass back to you to do some exercise. This one is the vector of size 3, right? And then there's an exercise for you to do a vector of size 1000. Remember? We did last week. Now you bring that program to here and then run. If you haven't done so, I suggest that you do, but you should have done it at home. Bring it back here to run here. Okay, so you can actually do it at home also, but I suggest you do it now. I'll give you 10 minutes to do. You copy it over. I show you all the skeleton code already, right? I put in all the comments and then you should add in the code back, right? So you bring it over. You can upload it if you want to, but I suggest not to upload because otherwise when you do the migration you've got a problem here. So I suggest that you put file, put the file inside. Okay? Now I want to show to you the first one first. The other one you do yourself. Okay? I'm showing to you this one. You're supposed to do this one, right? These two. But I'll show you to do this. I'm going to do this. For the serial one, I'm going to do for you. But the parallel one, you do yourself. Okay? And you do it now. After I show to you. I'm going to copy this. And paste it here. So this one is a serial one. That means we run using CPU. Okay? Try and slip in. You want to slip here with it? Okay, zero vector F. Okay, this one actually is not QDAP because we're going to run using our CPU, right? But then I told you before, MPCC actually can compile the code, so we can use MPCC. But if you don't like it, you don't want to use QDAP to MPCC to compile it, you can actually choose any one of these. Okay, so right now I'll show you alternative way to compile. But take note, when you compile with this, it's only compiled for our CPU. But it doesn't matter because this serial one is supposed to be executed by our CPU, right? Not the GPU. So I name it this way, .cpp. Okay, because I'm going to use G++ to compile it. Okay, it's the same, right? The command here and the command here are the same because the VCC actually is a variant of G++. They use the source code from here for their VCC. So the command here is the same. Okay, it's the same for Clang is different from this. It's a new project, but then because they want to make it compatible, so they use similar interface. So Clang and GCC, the way you use it is the same, but they are completely two different C platforms and C compiler teaching. Okay, so sorry. I'm going to paste it here. Right. Just do a run because we used to doing all this. Actually, you don't have to. Okay, I'm not going to change anything. I just leave the printf as it is at the moment. Just play it. Okay, run the file. And right now I can compile it. Right now I'm going to compile with G++. G++. The command here is the same. Let's call this 0 F. Go out. Okay, and then dot cpp. Okay, and I want to execute the program. Dot slash dot out. Okay. Compile and then run. Okay, the problem there is the malloc. Okay, in Windows, actually the malloc is also defined inside here, but for Linux, actually it's elsewhere. It is inside std. Because of this malloc free. It is in Linux. It is actually inside std. Okay, in Windows, actually it's also inside std. But then in Windows, this std will also include std inside, but not in Linux. That's why I have to include twice. I include here because it in the std.io, Okay, once done, now I can go ahead and compile. Then it give me the first end result. Okay, give me the first end result. So this result is correct, right? 0 plus 0 is 0, 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8, and so on and so forth. Okay? So I don't have to check the rest. I know that the rest of the 1,000 elements will be correct because the first time is correct. Okay, so I assume that it's correct. So I showed to you how to compile using G++. Okay? But later on when you do the parallel vector add, the parallel vector add is going to use GPU, right? So you have to use MVCC, don't use G++, right? Because it will not work. Okay? And then we want to do profiling. But right now, we have problem with profiling here because if you see, it doesn't profile for us. How much time that it takes? Okay, but for this, we can profile. We can profile using MV profiling. So we can see it, even though we don't have the right special code for it. And in the past, we use OMP get time, right? OMP get time, and then we find the difference, that is the duration, and then we print it out. Then it shows to us how much time that is spent in solving the problem. Okay? If you are using QDAP, then we just use MVProp. We don't have to write additional profile for you. So it's much simpler. Okay? So if we want to profile our CPU code, we have to write just like what we did last time. But unfortunately here, there's no OMP. If you want, you have to install the OMP. You can. You go to the batch and then install one by one. But I don't want to do that, and because it's not universal. I'm going to use the standard library to do the profiling for us. Okay? We can do the same without using OMP get time. Okay? How do we do it? Now I'm going to show you that. Okay, because I'm going to use C++ library, and I don't want to use this C program library. I'm going to change this to our screen. And of course here also I'm going to change this to C out. C out. C to C. Okay, and I. CI and line. Okay, so this is actually the same as the top, so I'm going to do that. Okay, because I use C out and I don't put std semicolon twice, I need to put using namespace, otherwise you complain. I'm using namespace std. Okay, so let's try to save us and then compile to see whether it runs. Yeah, it runs. That means it's correct. Okay, after this one is correct, even though I changed the CI. Okay, what I changed, string using namespace std, and then here I instead of print out, I substitute the CI. Okay. Now I want to use the next library, which is chrono. Chrono is a way to actually get the time. Okay. Instead of using OMP get time, you can use this standard library chrono. Okay. Chrono is also available, and this library is also available in Visual C++, Visual Studio. Okay, so that means if we run it, it should be running inside our Visual Studio as well. Okay, so we're going to use chrono. Chrono is actually a C++ library, and we have to use C++ and see how I got program with that. The first thing is I need to get the current time. And in order to get the current time, I need to store it inside a variable. And that variable is, I'm going to get the time here, start time. Okay. I need to create this variable, but let's put the code first. And it's called system clock. Okay, and it's a static function. That's why I put like that. I put this double colon, because this is a static method. Static method of this system clock. I'm not sure whether you learned static method. Do you know a static method? Maybe you learned it inside of Java. Anybody here learn Java? Yeah, you know static method, right? So it's the same thing. Okay, static method, that means you don't have to create the object first. You can use the class. This is a class name. Okay, because this is a static method, I can use the class name and then now. Now in Java you put dot there, but in C++ you have to put double colon. Okay? If it is an object, then you put a dot. But because it's a class, you have to do it. So this is something different from Java. But the concept is the same. So I said system clock is a class, and use the static method there. For now, we get the current time now. Okay? Now, how about this start here? This start is actually a variable, and this variable is of this type. Because this system clock now, we return the type, and that type is called time point. Okay? We return this type, time point. And then the data that it holds is double. Okay? I'm not sure whether you're familiar with this or not. Have you seen this angle bracket? I know that you've seen this angle bracket in CUDA. It's triple angle bracket, right? This one is single angle bracket. Have you used this before? This one is called templating. Have you learned templating before? Or maybe in Java. Have you learned templating? It's the same thing, template. Never? Okay, if you are not familiar, it's fine. Time point is a type of this start, but the data that it's holding is double. Okay, you can put integer here, but in this case, clock now actually return this time point. The data that you hold is double. Okay, that means it's floating point now because we want to put at 1.5 second, right? 1.5 is double, isn't it? So it must be double. Okay, so that is the start. It's a type. This is the class, the class name with the type double. Okay, and this is the object of this class, time point. And whatever that is written is actually an object. It returns it to the start. Okay, that's what it means. And then now I want to create the duration. So I create another duration here, and the person, the class is called duration. Okay, so start point, duration, system clock is all defined inside Chrono. Okay, if you want to define it. This one is another class called duration. And this duration, actually, we have to tell who is going to use this duration. It's actually clock, system clock. You're having the duration that, the class itself, what sort of data that we are using. Is a system clock, okay? And it's a period. We call it period. This is the name. And we get a system now. The current time at a period of time. So this current time is before method F. Okay. And after we have executed, we get the current time again. We subtract with the start, just like what we see in OMP. Okay. OMP we also do the same thing. Get the current time, subtract with the previous time, which is start. And then the result is placed, the result itself is actually the duration. And I put it in a variable called period. Okay, so this is a type of this period. And I tell this duration class who is actually using this period. This is a system clock. Okay? And now I'm ready to print the result. Print the time. Print the time here. Out. time taken is, and I pass in the period. But unfortunately, is you have to tell period to return the value, and you have to return it this way. Okay? It's not just passing the object. I think it's kind of silly as well. I'm not sure why they program it this way. I mean, why the period is programmed this way, I'm not sure, but you have to do it this way. To type period dot count. So this period is going to return the value inside here, which is the system plot. Basically, is this time. Okay, and then you print out the value. Okay, let's see what happens. You do this. Okay, and then play. Oh, it doesn't understand. Okay, I see now. I make this, copy that, using namespace. Namespace again, because I use the short form just now. Okay, Mara, I should be typing like this. Time point, it should be std, chrono, time point. I should be writing like this just now. But this is going to be very lengthy. I'm going to type like this. Only here, I have to do it here as well. So it's going to be very messy. That's why I put it here. STD chrono. So I have to append it at the front of every of this this top and whatever. Okay, once you've done that, then you can play again. Play this. And then play this. Oh, still a problem. It's a problem now. Period count. It's not a plus problem. I'm not sure what I've done with this G++, but I should be able to start this in VCC. See what's saying. Okay, so I have managed to get the report. Somewhere else there is not functioning. Yes, double here system running mistake. I put the reverse. Okay, I can put auto there, but just want to see some information. Okay, let's get back to here. This one is times time. Time is a plus. The plus is system. I put double there. Actually, it's wrong. It's not double. It should be mistake. Okay, and then here everything's correct. And here is duration, and so here it's supposed to be system clock. Should be double. Here is the one double. Let's save. Okay, now it works, and then it tells me the time. Okay, so this is a way to actually doing your own filing. You write it in the code, you get the time, and then it shows the. Now this one is quite small, it's 5 microseconds, so it's as fast as a GPU as well, but this one is a very small one. Okay, so you can try with parallel vector add. And parallel vector add is going to be executing GPU. Okay, and you use MV profile and then compare with this time to see whether the time spent is that function. Okay. Okay, give it 10 minutes to bring over your code. Okay, I show you skeletal code last week, right? Bring it here and then run the GPU. To see whether it works. Now, before we go into that, I want to show you something else. Because last week I realized that I gave you the wrong code. Some part is wrong. Okay, now I want to correct it.
也是一什么？
Okay, so copy over whatever that we have done last week. I made a slight mistake here. I showed to you this one here, right? And it's not really. I give you this information, this is not quite right. This one is not right. So I want to modify it slightly. This equation here is not right. Modify it. There's no in there, I made a mistake there. So I'm going to recorrect that. Okay, this one's supposed to be, let me write it down the correct one. This one is wrong. The old one is wrong. The correct one should be like this. It should be array size. Right. Plus 1, 2, minus 1. Divided by 4. Should be like this. And put a bracket there. Alright, like this. So I made a mistake there. Okay? For down below, I put 1024, right? 1024. So here 1024, here 1024, here 1024. Now for this also I made a mistake. Down below also I made a mistake. So you make that adjustment. So it should be array size plus power 2 minus 1 divided by power 2. Now this number here must be the same. If you choose here 256, it must be 256. This must be 256. And what does it mean and why is it like this? Actually, it's inside the largest slide, but I think it's chapter 7 or chapter 8, so it's still far away. I'll wait for that time. So I need to explain it now, otherwise you will not understand why is it configured this way. Okay, first thing is, let's look at the diagram first, because this one is crucial, because if you fail to understand it, it's very hard for you to understand it. Because the execution configuration is very important. So you have to listen carefully here. If you don't understand, please ask. I want to use this diagram here. Anyway, you can read here if you want to. There's one book that is quite good. I also used that book when I was learning it. QDA by example. I think it's, I'm not sure whether it's free. It's not free, right? I think the author actually posts the online version, just like ebook you can download it. QDA by example. Okay? Those two are the engineers, the software engineer for QDA. So they wrote that book. I find that book is quite simple. Okay? Not really simple, but then it's easy to follow. Okay, so I'm going to compress a little bit just to tell you what you need to know, okay, in order to compute this or calculate the thread size and also the grid dimension. Okay. Now the GPU actually has a lot of processor, so it has a lot of cores. One processor. there's a lot of cores out there. I think the latest one is about 1,900 plus. But they're not going to use all this because some of them are redundant, some of them cannot be used. Effectively, it's only about this much. But this number of cores is quite a lot because our GPU, our CPU don't have this much of cores. Okay, but the GPU has a lot of cores. The actual cores is this much, near close to 2,000. But the usable one is only this. Okay. Even with this, it's quite a lot. So imagine that. How are you going to manage this? Okay. So when you program, of course, you've got a lot of cores. But how do you tell this course to operate? How does it run? Okay, you need to map it. Okay, you have to map and tell the GPU how you're going to arrange this core to execute the program. Okay. The GPU that we are, the processor or the GPU actually use this inference taxonomy. It's called SIMD. Single instruction, multiple data. Okay, you got a lot of data, but the instruction is the same instruction. That's why you see the kernel is only one kernel, but multiple cores running it because this multiple core run in parallel. Right? But the data that comes in is actually different count of data, so it's multiple data. How about our CPU? Our CPU is actually SISD, single instruction, single data. Okay? And of course, you've got multiple cores as well. So we can have, in fact, our CPU is more flexible. We can do SISD, we can do SIMD as well, because you've got multiple core. You can do multiple instruction, single data, multiple instruction, multiple data. You can do all. Okay? So our CPU is more flexible, but the GPU is this concept. They use single instruction, multiple data. And it has a lot more cores. Our number of cores, I think maybe 8 or 16. Here you got 1,000 of them. Okay? Now, but then with this number of cores, you need to know, or you need to make it easy for the user to use it. Okay? So the CUDA programmer decided to use it this way. So grid, inside the grid you got multiple blocks. Inside the block you got multiple tracks. So this is how it's arranged. Okay? Okay, so you got a block, you define a block, and then you specify how many threads inside that. Let's say, for example, I want it to be 186 threads inside the block. Okay? And I can repeat this number of blocks here. Okay? I can repeat this. But the size, once fixed, the rest of the block will follow. That means if I put this 1 to 8, I cannot choose this block to be 2, 5, 6. It will be the same number of threads inside the block. Alright? And then in how many blocks are in the grid? Okay, is inside the grid. Okay? So I can specify two things. In a block, how many threads? In a grid, how many blocks? And the block always have the same size. Okay? Now, how does it run our program? Okay, let's have a look at our program. Let's take a simple one. Okay, a simple one, which is 3. Okay? This is a vector. And this vector, I got 2 vectors, and I'm going to add them together. Right? Add them. And finally, I get another vector. This vector is, so this is A plus B, sorry, A plus B, this B plus E, this C plus F. Right? So the thread is going to execute it. It's going to take A plus D and put the value inside it. So this is vector A, vector B, vector C. Okay, so we do that, right? And because we want it to run in parallel, so we ask the threads to do only one. One thread do only this addition and store it here. The other thread is to do this and add it here. So I got 3 threads running concurrently or in parallel. Then they can execute in one clock cycle. Okay? In CPU, no, CPU is going to execute this one by one, so it requires 3 clock cycles in order to do this. You got 1000, then you have to go through 1000 clock cycle. But for GPU, if you have 1000 cores, you can execute in one clock cycle. Right? The code is the same, but the data is different. That's why it's called as single instruction, multiple data strategy for this GPU. Is that? Okay, so how does it map to this grid and block? How does it map to this? Now I have this problem, and I know that I'm going to assign one thread to this, so I need only 3 threads, right? If my block is 1 to 8, that means I have more than what I need. Okay, I have more is fine, because I have an if statement to tell. The if statement will tell, okay, the first 3 will do, the rest don't do. That's why you see the if statement there, right? That means I can assign. Of course, I'm wasting my cores, but I can do so. Okay. Now in this case, do I need 3 blocks to solve this problem? How many blocks do I need? How many blocks do I need? 1. Yeah, he's right. You need only 1. You don't need 3. Yeah, I need only 1, right? And 1 to 8 is more than, actually I can put 3, but this 3 is going to be wasting also. You know? Imagine here it's already too much. I only somehow have 3 blocks. So if I specify the thread is 1 to 8, then here I do not need 3, I need only 1, because I only need 3 out of this 1 to 8. This is too much really. Okay? So if let's say I set it, the thread block to 1 to 8, okay? Number of threads in a block is 1 to 8. Grid block, that means the block, number of blocks that I need is only 1. Okay? Ideally, this one should be 3 only. 3 threads, 1 block. That's the ideal one. Better? But of course, I can put 1 to 8, 1. Okay? Or I can put 1 to 8, 3 here also can, but then of course I waste the processing power. Now, if let's say I got 1000, okay, and I set my number of threads in a block is 1 to 8. So how many grid do I need? How many blocks do I need in a grid? In this grid here, how many blocks do I need? Now my size is 1024. My number of threads is 1 to 8. How many blocks of threads that I need in a grid? How many? Come on, calculate. Don't stare at me, just calculate. Use your calculator. Huh? How many? 6. Are you sure it's 6? 8. Okay, you need 8. Is it just nice? 8? Do you have extra? No extra threads, right? Just nice. Just nice that you execute this. Okay, so how do you write here? If you know that your number is 1 to 4, and I set my number of threads, this one you can decide. So I set it 1 to 8. If I set here 1 to 8, let's say I set 1 to 8. Then here I don't have to write all this very complex formula. I just put 8 there. Because that is what I want. I want my number of threads is 1 to 8. Number of blocks will be 8. Then it will solve, and I don't need the, do I need the if statement? No, I don't need the if statement there. Because all of them will be used. I don't have extra, and I don't have less. And you cannot be less, right? Because if it is less, then your result will be wrong. Why? Because not enough thread to compute. Some of the result is not computed, so you get wrong result. You can have more, but you cannot have less. Okay? So the simplest one is to use the number directly. That means 1 to 8 here. Now if I change here. I change the number of threads to twice 6. Now, how many blocks that I need in a grid in order to solve the same problem? How many blocks do I need to solve the same problem? Huh? How many now? Yeah, it's 4. So I need 4. Because if you multiply this, you get 1 to 4, right? Okay? Then I'll do the same thing here. If I know the number here, 256, I just put 4 there. And your program will run nicely. Okay? Now, what happens if, let's say, I have not this number, but I have 125. 125. And let's say the number of threads is still 256. How many blocks do I need? 4 still? Okay, 4 times 256, what do you get? 1 to 4. But you need 1 to 5. Right? So 1 to 5, 1 to 4 of the threads will execute correctly and it will compute for you, but 1 less thread. And that thread actually didn't compute anything. Will your result be correct? No, your result will be wrong. So how many grid that you need? How many blocks that you need in a grid? Yes, you need 5. But of course you can see right now how much it weighs, right? How much it weighs this time?
255.
255. 255 thread is actually doing nothing. Because you just need one of the last block to execute that last one there. Understand? But this is common. Okay, it doesn't matter because this is how NVIDIA designer, they design this way. Okay? You can have more and you waste it, it doesn't matter, but you cannot have less. Because you have less, you will not compute the result correctly. Because you need enough number of threads to execute it. Right? Okay. Let's come back to this equation here. Of course, if I know this, I know this number, and I know this number, I can compute it. So I put 256 there, I put 5 there. But what if I don't tell you? I don't tell you this. Now you got a problem, right? If I don't tell you, I can just tell you n. And this n can be arbitrary number. Now you have a problem, isn't it? Now you have to do your computation like this. Because you have to compute. Okay? So let's see how we compute. If I want to know how many number of blocks I need, and n is given, so what will be the formula there? That means the computer will compute. Because when the computer runs, the array size will be known when it runs. It doesn't know when we run the program. Because the user is going to tell what is the n number at runtime, right? So we ask the computer to compute depending on what is given. Okay? So array size, let's say array size is n. So what is going to be the formula here? What is going to be the formula? Let's say it's given n. How many blocks are in it? What should it be? Huh? N divided by 256. Right? Okay. N divided by 256. What do I get? If I get my n is 1024. I get 1024 divided by 256. What do I get? I get exactly 4, isn't it? But if my n is 1025, I divide by 256. What do I get? Calculate and tell me what is the value here. Fractional number. 4.00396. Something like that, right? Okay. Now we know that actually it is more than 4. It shows to us that it's not enough. 4 is not enough. We need more than 4. That means we cannot use 4, we have to use the next integer number, which is 5. Which means we have to do like this. we take the ceiling of this number. Ceiling means whenever you got a fractional number, you take the closest, largest number, integer number, right? It's 4.1 or 4.000, no matter how many zero, and 3. If you take the ceiling of it, it should be 5, right? Okay, so the ceiling of it is in mathematical form, we write like this. Of course, mathematicians use this. It's easy. But how do you write in code? You cannot write like this in code, isn't it? How do you write it? How do you write this in code? How do you write this? Okay, let's see how we write it. If I take a number, let's say I take a number which is integer. Let's take a simple example. Let's say 9. I divide by 2. I know that this is going to be 4.5, right? But in C program, if I take 9, which is integer, 2 is integer, I divide them, what do I get? You should learn this in your C++ programming. 9 is integer, 2 is integer, and I divide these two numbers. What do I get?
4.
I get 4. I don't get 4.5. Because integer divided by integer, you give you integer, right? And it is always round down close to it. And we cannot use round down. We cannot round down. We get round down for free in C. You round down to 4. But what you want is to round out. How do we make a round out rather than round down using C language? Very easy. What you do is this. You take the n, you just add a little bit so that when you round down, you get to 5. Understand? What I mean by that is this. Let's take the example just now again. I got 1024, 2025, 256. And just now you tell me it's 4.0039 something, right? Yeah. And we know that this is bigger than 4, and we should use 5, right? So I can add this a little bit so that when I divide, even though I round it down, it will be 5 there. How do I do it? Okay. You know that 1024 divided by 256 is going to be 4 exactly. Right now? Okay? If I add with 256 divided by 256, this is 1. If I add this 2, isn't that 5? Is it 5? This one divided by this plus this one divided by this, you get 5, isn't it? The answer that we want. Is it correct? Now, just now it was 1025. Fair enough? What I need to do is, I just add with this number here, 256 here, and 256. What do I get when I divide? It will round down, but it will be 5. Fair enough? But I don't want it to be too big, because it's too big. Sometimes when you add, you round down to 6. You don't want that, right? It cannot be too big number. It's just nice. And you find out you don't want to put 256 there. Why? For this reason. If let's say I have, okay, this one will work for our case. But if I have like this, 1, 2, 8, 1, divide by 256. Sorry, I shouldn't do that. I should take 1024 plus 255. 1279. What do I get here? You will take this number. Give me in fractional number. What do I get there? 4 point something, right? 4.9 something. Is that true? What is the number? 4.996,
996.
isn't it? And when I round down, it'll be 5, which is correct. Sorry, it is incorrect. It's incorrect, right? Now, if I add 256, what is going to happen? And then I divide. I expect to get something similar, but do we get this number? I take this number, add to this, and I divide by this. I expect it to be 5. What do I get? Huh?
5.96.
Are you sure it's 5.996? 1279 plus 256 divided by 256. What do I get? You sure? 1024 plus 1279. And I take 256 divided by 256. What do I get? Yeah, I do get that. Let's see, I'm going to see that. Oh, sorry, I made a mistake. I should say this is 180, 1280. Okay, this one 128. Okay, and of course this one should be 5. Okay, let me repeat again. If this is 1280, right? What do I get here? I get 5, isn't it? But if I were to use this formula, because if I write in the code, it must add with 1256, isn't it? It must add with 256. Here, when I divide by this, I get 6, isn't it? So it does not round down correctly. It does not round down correctly. So how do I change this number? So that it will work for this case, it will work for this case as well. Okay, in order to do that, I need to subtract by 1. Yeah? If I subtract by 1, it will work here. It will be 5 for this. It will be 5 for this as well. Okay? Is it correct? Because if I divide this, I get 5.999 something, right? And then when I round it down, it will be 5, which is correct. Because 1280 divided by 256 is actually 5. Okay? So I cannot use this number directly, so I need to subtract by 1. Okay? So that it work for this and it work for this case as well. That's why this formula that you see is like this. Yeah. Right? So this is n. And then plus with this 512, because I divide by 512, here I divide by 256, right? So I need to add 512 and then minus 1. Okay? This minus 1 is so that it works for this extreme and it works for this extreme as well. Okay? By doing this, then I don't have to hand calculate it. We ask the computer to find out itself. Given n, what is the best size to use here? Okay, so you compute it for you and you compute the correct one. Not too much, not too less. Too less cannot because it will not give you the correct result. Too much, you waste a lot of blocks, which is not going to be used. Okay? So that is the reason for that formula. Now do you understand why this formula is there? And you have to memorize this. Because in the exam, there's no time for you to go through all this. Right? And you have to remember this is how you calculate it. Okay? Alright? Okay, so since you understand how this thing works, right? Now you can program, but before that, let's explain a little bit about I explained to you, you need, once the track blocks is defined, the size of the track block is defined, we can calculate how many blocks we use in the grid. But how does the GPU assign this block or these threads to execute your code? Okay, let's have a look at one example, which is a similar example like this. But I'm not going to use 3, I'm going to use 1000. 24. That's right. Some time back. Okay, I have, let's say I got, I make my thread number smaller. So threads, I have threads, let's say I have 4, okay? And then my grid size, that means my block size, number of blocks, I should say, is, let's say 2, okay? The reason why I have 2 is because I got 7. Okay, 1, 2, 3, 4, 5, 6, 7. So I do the same, the same addition here to produce this vector C. Okay, so this A, B, C. So it's going to add and put, right? Because my thread, number of threads in the block is 4, number of blocks is 2, so if you multiply it's 8, isn't it? Is it sufficient for this 7? More than sufficient, right? Because it is 7. So one of the thread is not going to be used, it's going to be wasted. And therefore you see this, that's why you see this if statement here. This if statement is to do that. Right? The if statement is to tell if your thread ID is bigger than a certain number, which is bigger than this, don't do anything. Otherwise, you do this job. Okay? Because of this problem. If let's say here is 8, then I can remove the if statement. Right? But of course, if the if statement then is more universal, right? It will work for all cases. Okay? So let's see how it is assigned. So whenever you create this kind of thread, the GPU will assign the string processor. Okay? You will call it SM. The string multiprocessor to this thread so that it executes. So one thread, one core. And how many string processor inside there? It can be 32, it can be 64, depending on the technology or the version of the NVIDIA GPU. Okay. So it will assign this string processor to this thread to execute it. Okay. Now it can assign 4 because you see 4 there. You assign this 4 there. Okay. And you compute it. Then the other 4, you assign another 4 to another block. So these 2 blocks can execute maybe one by one, or it can execute at the same time, depending on whether the string processor is enough. In our case, let's say string processor for this processor is 32, let's say. Okay, 32 in one block. Then it is enough, because all of them will be executed at the same time. Okay? But let's say if my number is very small, let's say it's 4, say it's only 4, then you can see already, only 4 cores can execute at the same time. Then the next block will be executed by the same core in the next cycle. You understand? But if it is enough, then you assign it. Okay, so that means this block is going to be executed at the same time, or it can execute at different time. The first block or the second one, right? Or it can be when they execute, it depends who is faster. Then you get the result. So we cannot determine which one will appear first. Okay, because everything is executed in parallel. Understand? Okay, so that is how it is executed for this. All right. If let's say, for example, I have 2 dimensions, for example, in this case. Now, how do I solve this problem? Because this one is later part, we have to implement it. 1 dimension is like this. We use only the specific threads to actually execute it. But in 2 dimension, then you have to look at it in 2D. Okay, one in X. Sorry, this one is X. This one is Y. this X, this Y. Okay? But the number of threads is still the same. That means if you can view this thread in linear, that means this one is next to it. Right? So it's one big size of threads, but it's organized in this way. Okay? And therefore, you need to find out which thread is actually executing which row and which column, and then you multiply. Okay? So let's talk about the simpler one rather than this complicated one. Okay, for example, in this case here, if I want to find out which of these element that I execute, okay? If I'm using thread of 4, number of blocks is 2, okay? Because remember what I mentioned to you, if you organize it this way, then it will affect your programming. Your programming will depend on the size here and the size here, okay? So I say 4 in a block, and the number of blocks is 2. So when you execute, the GPU is going to assign the string processor to execute this as a block, which is a block of 4. Okay? So the block of 4 will be appearing like this. The thread number is 0 to 3. 0 to 3. Okay? And the block ID is going to be 0. In the first one, it's going to be 0. So this is going to be executed as block ID equal to 0. Okay? And there are 4 altogether. And the second one is going to be executed by block ID of 1. So this is block ID. Okay? And the thread number is going to be 0, 1, 2, 3. And this is going to be 0, 1, 2. The 3 one is not going to execute anything. Okay? But the number is 0, 1, 2. 0, 1, 2. And this block ID is 0, this block ID is 1. Okay? Now, when I add all this, I need to calculate. Okay? For example, in this thread here, thread 0, but block 0. That's why block 0 multiplied by block dimension. The block dimension is 4. 4. So 0 multiplied by 4, what do you get? 0. And then you add by thread ID, which is 0, what do you get? 0. So it's this index number that you're looking at. Okay. How about block ID 0? We are still in this block. And then its thread ID is 3. 0 times 4 is still 0 plus 3. So it's correct. It's this block. I mean, in this element that is supposed to compute. Now next, because right now we are looking at the next block. But then it's going to be executed by this 0, 1, 2, 3 again. Okay? And it must be correct, right? You must select the correct element and pick. So let's see. Thread ID is 0 because it's this 0. But block ID right now is 1. 1 multiplied by 4, what do you get? It's 4. Right now you're here. Plus 0 is going to be here, so it's correct. But it's going to be executed by thread number 0. No? Understand? So the thread ID is actually the index number of this problem that you're trying to solve. Understand? Although the name is thread ID, actually you cannot imagine it's a thread ID. It's actually the index number of this vector. Okay? And whenever the thread is executing, it has its own ID, thread ID number. Right? And then the block that is executed is also given as well. At first, the fourth thread is going to execute in iteration 0, and then iteration 1. And when in iteration 1, you have to multiply by 4. Okay? You cannot multiply by 0. You multiply by 0, that means you're resolving this problem. No, you're not really going to do that. You're going to execute the next one. Okay? You understand? Now, if let's say I change this to 8, and this one definitely it should be 1, right? Okay? Right now, I just changed the configuration, but now the programming will be different. Why? Because right now, here, you're not going to see it as 2 blocks. You're going to see it as 1 block. And right now, you got only one block. That means you got 0 here, multiply by 8, and then add with the track ID. Because the track ID is going to be 0 to 7, isn't it? So 0 times 8 is 0, plus 0 is this. And you do it until the 7. 4, 5, 6, 7. Another one is on that instead. Okay? 0 times 8 plus 7 isn't it there? Still there, right? But you're talking about one block. And this equation still produces the same result. The same result as 4 threads, 2 blocks, or 1 block, 8 threads. You understand? Okay? So this formula actually is universal. No matter what kind of arrangement that you do, you calculate for you the correct index number of this solution. Okay? Now if you understand this, then now you can try to tackle the two-dimensional. Now the two-dimensional, there's no difference from that. We're going to calculate this, the threads ID in 2 dimensions rather than 1. Okay? So when you multiply, you have to multiply correctly. So here is going to be 1 dimension, and this is another dimension. Okay? I don't have enough time. Finish at 1:30. Okay? You go back home. Okay? Try this. Now you know how to calculate this, right? How to put the number inside. Right? You can choose any track ID number here. Okay? Now I suggest the number should be multiple of 1 to 1. It cannot be too big. The maximum size here is 1024. Okay? It cannot be bigger than 1024. Okay? So you choose any number. It cannot be 0, of course, but it cannot be bigger than 1024. So you choose 1, and then the formula here will calculate for you the real number problem. Okay? And then you solve the problem. Now, look at the time. How much time that you gain using GPU and CPU. So, okay? So this is for your home exercise. And once you finish it, you can try this matrix multiplication. Okay? Now, the matrix multiplication, when we do, you see this, there are 3 here, right? 3 numbers, right? So this is the x, this is the y, this is the z. Yeah? So let's say if I choose this one to be 1 to 8, right? And I can choose my y also 1 to 8. Okay? And when I compute my grid, I also can compute it this way, something similar. So this one is 1 to 8. Okay? And this is going to be the same for this. Understand? Okay, it depends. Let's say, for example, this array size is for the x, and this array size for the y. Let's say, for example, you have these 2, right? And if you want to use the same number of threads, you can change. And this is going to be this. Okay? So this is going to be the x dimension, this is going to be the y dimension. Okay, this array size for the x, let's say for example, your array size here is different from here. The size is different, then you're going to choose 2 different numbers because your matrix size is different, right? And the x is this, because 1 to 8, you divide by 1 to 8. But here is for the y, which is 2 by 6, and then you choose this. Okay? Of course, you can choose 1 to 8 here also, it doesn't matter, even though here is the size is different. But if this is 1 to 8, then make sure that it is 1 to 8 as well. Is that clear? Okay, so this 2 dimension, of course, you can go 3 dimension as well. For 2 dimension, you have to use this for so on. Okay, I'd like you to try first. Let me see if you're able to solve it. Okay, you can go now before that. 인용, 심수생, 차승희, 김자만, 강웨성, 더마다시니, 다시니, 더마다시니, 다시니 하고, 우에리, 우에리, 잭슨 차이, 로영진, 리신하이, 리웨슨, 웨슨 here, 린샤이, 린웨한, 남춘호, 남춘호, 남춘호 위순, 어디 있구나, 순, 위순.